Okay, so here it is, the sound now. Yes, I sorry, my mistake is my mistake. So there was no sound because just press the button of not showing the sound. Okay, yes. Okay, I see your messages there. Yes, so the thing, it's about, today it's about teaching how to program robots that can learn by themselves, how to program themselves. So that's the basic subject. So it is the future of robotics. Instead of using computer programmers to program the robots, the future for me is that robots that train by themselves, that they learn how to do the things. And this is the subject that we are going to do today, okay? And today the question is brought by Sophie Lin from Singapore. And her question is, how can I use OpenAI to train robots that work with ROS? So that's a very nice question because it's about how to train robots. And specifically in this case, it's about how to train robots with OpenAI. And by using, of course, by using ROS, because that's a framework that we like, all of us. Okay, so let's see first, indicating what is OpenAI. So OpenAI, it's a framework for training agents. It's, by agents, I don't mean robots, only robots, but any kind of computer program. So an agent can be a computer program that plays in a Super Mario game, or a computer program that learned how to negotiate with other computer programs, for example. So that those would be agents, are systems that want to act autonomously. In this case, we are going to apply this for robots. Robots is just an instance, is a specific case of agents. Okay, so we are going to see how to apply OpenAI for making robots learn by themselves. How? By interacting with the environment. Okay, so we are going to see this right now. And in order to train those robots, we are going to use a very specific learning technique that is called reinforcement learning. Reinforcement learning, let me show you this question, this image that I have here prepared. And in this image, you can see the basic schema of an wait a second, looking here. Okay, so application window, and yes, here it is. Okay, so this is the basic schema that you can see that you can find when you are trying to use reinforcement learning. Okay, so here you have the agent that in our case would be the robot, and then you have here the environment. That's the place in which the robot is set. The robot is working. Maybe that environment is the cafeteria where the agent has to bring the coffees to the table. Okay, so the agent produces an action, and this action inside this environment generates some specific state of the agent. Okay, so that state has an associated reward. So by the robot doing this action in this environment, we have assigned that that specific situation requires a specific reward. And then we observe what is the final state in which the agent and the environment have reached by applying this action. Okay, so we use this reward and this observation to learn, to make the agent learn and improve his action for the next step. And we repeat this cycle as many times as is required. So finally, the agent learns how to serve the coffees in this specific environment. Basically, that's how OpenAI works. And in case that you are interested in looking more about OpenAI, you can visit this webpage here, openai.com, and it's here where the OpenAI algorithms are set. And you can download them and use it. So in this case today, because we are going to apply OpenAI for robots, we are going to use another package that is created by early robotics that is called the Gym Gazebo. The Gym Gazebo is a wrapper of those OpenAI libraries in order to allow to use the OpenAI algorithms and classes and all the environment that OpenAI has developed, but for robots with ROS, and using Gazebo as a simulator for simulating here the agent, that would be the robot, and also the environment. Okay, so we are going to mix both things. First, OpenAI, and then this Gym Gazebo from early robotics. Okay, great. So far, so good. And so that is what we are going to do right now. Then, in order to show you this, how it works, today we are not going to use the ROS Development Studio, but instead we are going to go to the Robotic Night Academy that you can see here. And there we have a specific course teaching in more detail how to do this OpenAI Gym for robotics. But today I'm going to show you how it works and how you can reproduce this and program, modify the programs for your own robots and your own environments. Okay, so let's go for that to the Robotic Night Academy. Let's launch it, the course for OpenAI Gym, and let's go step by step and see how it works. Okay, so first, let me share again the screen with you. And I'm going to share this screen, share here. And then I went already to the Robotic Night Academy. I have already set up everything for you, so you don't have to wait. And in this course that is called OpenAI Gym for Robotics 101, in this course, when we run in the first unit here, we reach this environment here, okay? And just let me check that everything is working properly, so no problems with the maybe with the wait, yeah, here it is. Okay, so we have this robot in this environment, and then let's assume that we want this robot to do something very simple here. It's just to learn how to move in this environment without crashing against the walls. So that is the job that we want the robot to learn. Okay, very simple. This is a Turtlebot that contains the typical ROS interfaces that you can check here. So let me put it bigger. So if we do a ROS topic list, you will see that we have the command bell typical for sending the velocities, the odometry, the TF, all the typical, the camera, all the typical topics here, the cameras is here, the typical configuration of a Turtlebot. Okay, so you can apply this directly to your real Turtlebot. Then we have this Turtlebot here in this environment, and we wanted to learn how to move around here without crashing. For that, we are going to use the OpenAI Gym and with the wrapper for the Gym Gazebo. Okay, so here we have a simple instruction that we have already prepared. We are going to go afterwards after the inside of that, but just let me show you how it works. Okay, ROS run. I'm going to run this command here in the shell. Let me move away from here so we can see what the robot is doing. Yeah, and I'm going to run the command here, and let's see. So I'm running. Then now the robot should start moving after some initialization. Okay, then it starts the game position, and then it moves. It actually, now the robot doesn't know anything. The controller for the robot has been initialized randomly. So those actions that you see that the robot is doing mean nothing. Those actions are just random actions. But the important thing is that the robot is learning from those random actions. So the next step, on the next trial, he will try to reproduce those actions that he has done on the previous one that have delivered a very good reward, as you mentioned, as I mentioned previously. Okay, so then what you see are different episodes of the same learning algorithm. Here you see that every time that an episode has finished, then the robot is set back to the initial position again. And every episode, you can see here on the right bottom corner, you can see the result of each episode here, and including the reward that has obtained. So the reward, if you remember here in the image, is the agent. We have the agent, that is the robot. The agent is taking actions, that these are the movements of the robot, and then these actions have a result in the environment that it is. So the result is the robot moving around, as you can see here. Okay, and then based on that result, we get a reward and an observation. So the agent can take this observation for the next action and repeat and decide another action that maybe is better for that environment, and then repeat. At the end, it will obtain a reward based on all the actions that has done. Okay, so concepts that you need to have clear in this case. First of all, we have the training environment. The training environment is all this place is. It contains, we include the robot and also the environment by itself in the simulation. I mean, the place, this maze that it is. So you can change the robot, you can change the maze if you want. That depends on what you want to train. Then, second thing that you need to know are the episodes. The episodes are trials that the robot is in which the robot is exploring what to do, what it can do, and what are the effects of its actions. These are the episodes. And during the number of episodes, the robot it's exploring what he can do. And we have a given number of episodes that we define ourselves. The number of episodes will depend on how fast the robot can learn for the task that you have associated. And in this case, now that the algorithm has finished, as you can see, we have set 10 episodes only. And for each episode, we have a reward. That's the reward that we have here for each episode. Here. And here you can see for episode number 7, okay? So every time that an episode is finished, then the robot is set back to the initial position again. The learning algorithm is modified. So the learning knowledge, I would say, the learning algorithm is maintained all the time. But the learning knowledge that in reinforcement learning is called the policy is updated. And then the robot tries again in the next episode. So the goal is that each episode, the robot will perform better and better and better and better. In this case, when the robot collides against a wall, we are considering that the episode is finished. That is why you can see here that episode 8 has finished, episode 9 has finished, etc., because the robot has collided. And in this case also, you can see that the robot has not learned yet to move along the whole environment without crashing. Yeah, that is because we need a lot more episodes than 10. Okay, so that's the reason why we cannot see this in just so few. Maybe we'll need 1,000 in order to learn that. Okay, so then this thing is the episodes. Another concept that you have to learn is that the number of steps, the steps of actions that you allow the robot to perform before we consider that an episode has finished. So imagine that we are in episode number 9, and then our number of steps is 500. This means that in this episode, the robot is allowed to do 500 different actions until we consider that this episode is finished. And we have also another condition that is about when the episode is finished. That is, as I mentioned, when the robot has crashed against the wall. When it crashes against the wall, then we consider, okay, no more actions, even if you haven't done the 500. Okay, so these different concepts are episodes and steps. So steps are the number of actions that the robot can do in one episode, and episodes is the number of times that the robot can try to do the same thing and see it better, okay? So then we have the learning algorithm. It's another concept that you must understand. The learning algorithm is the algorithm that allows the robot to learn. In this case, we are using a Q-learn algorithm, and you are going to see how it works. Okay, so let's go and see basically how this works. And for that, I have prepared here the code. So we can see here the code, that how it works, okay? So basically what you need, it's a Python file. In this case, we call it simple qlen.py, and we have put inside a package here. And apart from importing everything that is necessary, we have here the main program that is the one that controls everything. What do we have here? First, we load an environment. This environment is the file that defines which ones are the actions that you can do, how you can perceive the world, and any other related information required for the robot to learn based on his actions on the world. So this file, we are going to see just in a minute how it is created. This is basically what sets up the whole environment that we mentioned here. Okay, so it's this environment here of the reinforcement learning. So you have to define in this file several things, and we are going to see in just in a minute. So we load this environment that describes how the robot is able to move and to perceive in the world, and then we move forward. Then here we create a monitor. This monitor is very interesting because it's the one that allows you to record the data that is being generated during the training. So later we can plot and we can show how good the training is going, if the robot is learning or not, if the robot is performing better or not. Then what else do we have? Yeah, here we create an instance of the learning algorithm that we are going to use. Okay, in this case, we are using a Q-learning algorithm. There are many other algorithms of reinforcement learning that you can use and that are already implemented, like, for example, SARSA, that you can use also. And you can go and OpenAI and check all the algorithms that are already made there. Okay, so you create this algorithm and you provide here some parameters. And this first part of the parameters are the action space. This means the actions that the robot can perform. And these are defined, as I have explained, in the environment here. We are going to see this later. Also, you are providing some other parameters required for the Q-learning algorithm. I'm not going to get into detail of those parameters. Just go to the Q-learning algorithm description, and you will see very clear what those parameters mean, are very, very typical. Okay, then what else? So once we have this set up, let me repeat first the environment and then the Q-learning algorithm. By doing this, we have set the whole thing here. We have the agent, that is a robot that we have. We have the actions that can do that are defined in the environment file. We have the environment, the set of files and the set of actions and the perceptions that the robot can do. And then we have defined also the learning algorithm that modifies the brain of the robot, of the agent, based on the reward and the observations. Okay, so once we have this, we can just start doing what? The steps. Wait, first, we initialize here. There is a 4 for the number of episodes. Remember that in this case, we specify that 10, the number of episodes. we have this as the number of episodes. So every time that we finish this loop here, the robot will be set up again to the beginning of the position of the environment and start again taking actions. And here we have the number of steps inside the one episode. So we have an episode here that is running, and then we allow in this episode to take max range actions. In this case, is 1,000 actions. So the robot could do, in theory, 1,000 actions before this episode is considered finished. In our case, it was not necessary to reach 1,000 because the robot was crashing against the wall. Okay, so how does it work, this whole setup? Once we have everything set up, how does it work, the learning? So basically, first, we pick an action based on the algorithm. And the algorithm chooses the action based on the current state of the robot. In this case, the state has been initialized here to the initial observation. So this is the initial observation. It's just the robot starts at the starting position. Then based on that, we provide the current state to the learning algorithm. And then the learning algorithm selects an action based on that state. Okay, the state is here. What we call the observation is the same. It's the same, basically. So this agent algorithm, Q-learning, based on this observation, selects an action. Now we are going to apply that into the environment. How do we do that? Okay, so we have this, and then we apply in this line, we execute the action in the environment. Okay, in this step, this has nothing to do with reinforcement learning. The reinforcement learning action was taken here. So this is just about the environment. So we take the action that we have selected here, that this action could be something like move forward. This action could be something like turn left. This action could be something like go backward, in this case, for this specific robot, okay? We are going to see in a minute how these actions are defined in the environment file. Okay, so once we have selected the action, we apply here into the environment, and then we observe what happens. By applying this, what we do is just to apply this to the robot, and then the robot, based on that action, will move to one direction, to another, will crash against the wall. We don't know. It depends on the situation when this is applied. And then, so this just calculates the observation, that is the result. What is the result of this? Then it also calculates the reward based on that action. And then also it checks if this has been done because the robot has crashed or not against the wall, in our case. If it is not, then the reward is accumulated and used for afterwards. And then, basically, based on this result, we make the learning algorithm to learn. And we provide, what do we provide? The previous state prior to this action. Then the action that we took, and then the reward that we obtain by applying this action to that state. And also, what is the next state obtained? The next state is basically the observation provided here by the environment. Okay, so we use this to make the algorithm learn. How this works is just how the Q-learning algorithm works. So you have to go there and to the theory of Q-learning and check how it works based on that. This is already provided by OpenAI, so you don't have to do it. Great, so we have learned based on our action, and then basically if we have not done because we haven't crashed, then we just move to the next step here, and then we repeat again. Okay, based on a new state, we choose an action, we apply this action to the environment and see what happens. If the robot crashes, if not, it keeps going, calculate the reward, learn based on this action, and if it hasn't finished, then because it hasn't crashed, then we repeat. And then we repeat this until the robot crashes or we achieve the 1000 number. So basically, that's it. There is nothing more. There are a lot of here things related to different values calculations, but this is not important at all. So this is basically the procedure that executes this to make the robot learn. Then the whole learning policy, it's accumulated here in the instance of the Q-learning, in this Q-learn that we have defined here as a Q-learn function. And this is provided by OpenAI. Okay, so it's defined here. Let me see. Import, well, it's here, import Q-learn. This is imported from OpenAI. Okay, so far so good. Let me see if there is any question on the chat that I can answer. And then let's see. So we have, okay, Epson Warco was saying, please, let's try reading his lips. Yes, when I had no sound. That's very funny. Ha, ha, ha. Great. Then we have any other question? Let me see if there are more questions. Let me see. How a crash is defined. A crash, it's a very good question. I cannot pronounce your name because it's written in Chinese characters, but a crash, it depends on the application, okay? In this case, we have defined a crash when the robot sensor, the laser, detects one object at less of 0.2 meters. So at 20 centimeters of the position of the laser, because the laser is located in the center of the robot. So if there is something that is 20 centimeters to the robot, then it means that the robot has crashed. We consider this crash, but you can do it in many other ways. For example, when the bumper detects a bump, then, for example, because you have access to the sensors of the robot. But in this case, we have defined in this way. And you are going to see now in the environment file, okay? Is this available in C++? And okay, so not that I am aware. At present, I think that it only works in Python, and OpenAI, basically, they work in Python. But take into account that what you are learning here, it's for the learning process. So it's not during execution. So once, the idea is that you make the robot learn, so it generates a policy that allows you to make the robot behave in the way that you want. So you make the robot learn how to serve coffee, for example. Then in this case, speed, it's not the most important thing. The most important thing is that the robot actually learns and improves with time. So once you have that, the robot has learned, you have the perfect policy that allows you to just to take this and put it into the robot, so the robot can use it. At that time, you can make the conversion from that Python policy into a C++ policy, so then it will go very, very quick, because it will be in runtime, not in learning time. So you have to differentiate between those two states, learning time and runtime. How to simulate, Scam Miamba says, how to simulate real sensors, say HCSR0. Okay, so I cannot answer that question. So it's just a matter of getting into the simulator and try to reproduce it. I don't know which sensor is this. It's a LiDAR. It's a I don't know. It's a image sensor. I don't know. In Gazebo, you have many types of sensors simulated, like IMUs, GPS, bumpers, sonars, point cloud devices, images, lasers, LiDARs, and many, many types. So you can simulate a sensor. Even you can include the noise of the sensor into the simulation even. So it's just a matter that you put the effort on that. So I don't know this specific sensor that you mentioned, but maybe you can approximate with something that is already done also. Then Scan Nyamba says, is it possible to implement sort of continuous learning? Then yes, of course, you can do it. Then it would mean that the robot will be all the time, but that's a little bit dangerous because the robot can, based on what happens around, can learn a policy that is not good. Even if it has learned something that is good, then afterwards it can learn something that is not good. And then you will discard all the efforts that you have taken before. So continuous learning is a difficult subject. It's possible, but it's a difficult subject. And there are no more questions, so let's go and let me show you how to build the environment file, okay? So that's the next step. So I'm going to share with you the window, and let's continue. Okay, so this file that we have here, the gazebo circuit talked about 0, this is not a file, okay? This is an environment. And this environment has been defined in this file. Gazebo circuit tartebot leader.py. And here is where we define this class. That's the class that defines the environment, and that class inherits from this gazebo environment class, okay? Yeah, so that's the one that has the structure that we have to follow if we want to build our own environments. And so for that we have to inherit from here. Okay, so what do we have here? We have the init of the class, where we specify first the launch of the simulation that we want to launch. So this is a simulation that contains the robot and the environment. In this case is this maze that we are going to use for the training. Also here is where you make the connections to all the systems of the robot that provide you information, like for example the lasers or the data that you're going to use. In this case, we only need to have the command bell, in this case, for providing commands to the robot. Okay, we also are connecting to those services so we can pause and unpause the physics at every point in time, every time that one episode is finished. And every time also that we create an action, we send an action to the robot, we allow it to move, and then we stop the physics for a moment while we are doing the calculation. So the robot doesn't keep moving while we are doing the calculations of the learning algorithm, and we don't interfere. Okay, so this is the initialization of the environment, and then there are many things here. I'm going to explain you later, but the main point of this class is the step. This step is the function that is going to be executed when we allow the robot to take an action. So here, in this, if you remember these two loops, the first one is the episodes loop, and then inside every episode, we allow the robot to take an action. Okay, so here is where we indicate the step. And then this step is the one that executes this function here. So it's the step function, as you can see, of the environment. Okay, so here we have an instance of the environment and we apply the step function. And basically after everything that inherits from one class to another, finally you get into this step function. Okay, here is where you define what every one of the allowed actions can do. So in our case, for our robot, we have identified that we only need to allow 3 possible actions. But that depends on your application, okay? What you want the robot to be able to do. In our case, we allow the robot to move forward, to move to the left, and then to move to the right. So in this pool of the Q-learning, when we choose here an action, we are choosing only from those 3 actions. Then this action is provided to the environment and applied. So this is, if the action is the number 0, it means that it's a forward movement, and then we set the velocity to move forward here. If the action is number 1, then we move to the left with a little bit of forward. And otherwise, for if an action number 2, then we move to the right. That's it. Then on the next thing, the next thing that we do is that we read from the laser. We read from the laser in order to identify if we have crashed or not. This is related to the question that somebody on the chat has said, has asked, how do you detect that has crashed based on this? So in this place is here where we identify if the robot has crashed or not. So here first we get this laser scan, and we get the laser scan, and then this laser scan that is included into this data is provided to this discretized observation function. Okay, so what is this doing? This is doing the following. Let me see. Discretized observations is here, and then what it does is to discretize the first it detects if the robot has crashed. Okay, so if basically if any of the data ranges here is less than the minimum range that has been defined here as 0.2, then it means that it has crashed. So we'll set the done to true. Otherwise, what we do is that we discretize the values of the ranges. This means that we have reduced the amount of rays to just a set of them. And it's like making detection by zones. Instead of having 700 rays, we decided that we want to have just a few number of rays in each direction. And that's all. That's all. So this is the discretization of the laser. And we provide that as the observation. So this discretized laser is the observation that the algorithm, the Q-learning algorithm, is going to use to decide the state, the new state that it is. So we provide in this function, we return the discretized ranges, and also either if the robot has crashed or not. Okay, so we are here. So we have the state and the done. Then if it is done, if it is not done, sorry, then, and if the action was 0, then we define here our reward, that is 5. Because, why? Because we want the robot to, when it has to select options, then we want it to move forward. Forward is faster, forward is nicer. It means that it doesn't have anything in the front. So we provide a big reward when the robot is moving forward. Then if the robot is not moving forward, it's turning because the action is not 0, then we also provide some reward. It's not as important as the moving forward, but we provide some reward so the robot is still moving. So it's not stopped, it's not crashing. And then if the robot has crashed, then we provide to -200. This is very bad. Okay, so now you can see how this works here. Based on the environment, on the application of the action in the environment, that is exactly what we have done here. We have applied the action into the environment because we have moved it. Then, based on that, if the action was moving forward, we provide a reward of 5, or a reward of 1 if it has turned, and if it has crashed, a negative reward. Basically, that's it. This reward here, reward, and then we obtain the observation. That the observation is this state, is this one here. Okay, and here it is. So the state is the discretized observation of the laser. And that's it. So basically, that's the function in the environment that we have defined. That is the function that takes the action, applies on the environment, and then based on the result, calculate the reward and the observation, and then provides this to the agent. That the agent is the previous function that is calling it. Okay, so, and it's providing here. So this function here of the step, this step function provides the state, reward, and done, and then it returns here. This is the state, reward, and done. And then, so we keep doing the thing that I have explained you before. And we use this for learning here. And then if it has done, then it finishes the loop. If it's not finished, then it keeps doing more steps. Wait, where is the steps? Here. Yes, here it is, until it has finished, etc., etc. So basically, that's it, how it works. So I know that there is a lot here, and that we may need some more in detail in order to understand better this. But basically, that's what I wanted to explain to you. And I would like to see if there is any question for what I have explained. And I'll be happy to answer that. So let's see here on the chat if there are some questions. Yusuf Nadine says, you can gather data and make the agent learn in offline mode. Okay, so it depends on what you mean by offline mode. Okay, so if you mean like grabbing a ROS back that contains all the data of a robot moving around, and then you use this data then to feed into the reinforcement learning algorithm, the answer is no. Is no, because you need to get the feedback of the robot action. So, and the action cannot be predicted beforehand, because it's the learning algorithm who is going to decide the action on that at that moment. Then, if you mean by offline that you are not doing into the real robot, but that you are doing in a simulation, the answer is yes, because you have seen it just right now. You don't have to put it in the real robot and get this data on the real robot. You can do it in the simulation. Also, the simulation doesn't have to run in real time. It doesn't matter the time here. Time is not the matter if you are consistent on any step, okay? So the time is consistent. So just to answer that, you cannot use ROSBACs for that, because you need the data that is generated when your robot takes an action. And this data is not existing in your ROSBAC, because it depends on that moment, on the action that you take. And then what else? It's a sonar sensor. Okay, Epson Warco is talking about the HCSR04. It's a sonar sensor, mostly on Arduino. Yes, so you have a sonar sensor that exists on Gazebo. It's a sonar plugin. So you just go there and take it. and use it. And if it doesn't, you say, okay, yes, but it's not like that. In my case, this specific sonar has some specific specificities. Just modify it. You have the source code of this sonar sensor, so you can use it. Why to discretize the laser range values? Yes, this is because otherwise you have too much data, and then the space of possible states is too large. And for this specific task, doesn't make sense to have so many possible options. You will have one option per each laser array. So we don't need that. We can discretize and say, like, for example, you can even discretize to even a lot shorter number of states. You know, like only there is an obstacle on the left, there is an obstacle on the right, and there is an obstacle on the front. That's a discretization of 3 states. That's very simple. Well, 3 and the combinations of all of them, 9. Then, if we have 768 rays, like Hokuyo, for example, then that increases a lot the number of states. Then the learning of the policy, it's a lot more difficult. It will take a lot more time because the robot has to visit many more states in order to create a map of the possible decisions that it has to take. It's a very good question, by the way, Scammy-Ambas. What is the intent of another question of Scammy-Ambas is, what is the intent of gazebo pores on pose physics? That's also a very, very good question, Scammy-Ambas. It's a very good question. But this is not, those questions, I mean, are very good questions because they are not clear when you start what you have to do, but they have a huge impact in how you achieve or not to make the robot learn. And then why is the intent of gazebo pose and unpose is because it happens that we take the action, okay? We decide this action, move forward. Okay, we decide this. Then we bring this action to the robot, simulated robot, and we provide it. Then the robot starts to move, okay? And then we observe what is the status produced by this movement. Let's say that it's a movement of 1 second, okay? So the robot moved for 1 second, taking this action, then we observe, and based on this observation is how we are going to calculate the reward, etc., okay? So imagine that we observe, and then we start discretizing. We start applying this to the Q-learning. We check if has finished the step, the episode. We check so many things, and during this time, if we haven't paused the physics, the robot is still moving. So when you do all this and then you decided on the next loop, what is the next action? The next action that you are deciding doesn't correspond to the real situation of the robot because the robot has moved since you did the observation. So you are taking a decision at that point in time based on an observation of the past, but not an observation of the current state, you know? And then that is why you have to take the observation, you stop and then, you take the observation and then you stop. So the robot doesn't move anymore. So the physics is like the world is stopped. Then we do all calculation. It could take this calculation, for example, let's say 3 minutes, because it's very complex learning algorithm, 3 minutes. But then the next 3 minutes for the robot is like if nothing happened. It's like just 1 second was previously 1 second was taking the previous action, you know? So that is why you have to unpause in order to provide the next action. The robot moves, you sense, and then you pause again. So you can do all your calculations without, and the robot stays at the position where you have sensed. Okay? I hope that this is clear. If not, please ask me. More question, Epson Warco. How is discretized laser range values used during and after learning? Okay. Wow. Okay, so that's difficult because I haven't shown the Q-learning algorithm. And I'm sorry, but I will have to wait until the next week because I think that this is the web live show that has taken more questions. So we are about to finish. We don't have more time for today. And then what we are going to do is that we are going to do a second round of OpenAI applied to Gazebo. And what we are going to do is, based on your questions, we are going to practice all together, okay? So please, I'm going to send my email to provide you on the chat, my email right now here. And you send me an email if you want to practice on the next week. So we'll practice together during the live show. And then we will create all those packages, all those code for training this robot. And then I will answer also these questions. So you will be able to see how this discretized laser range is used inside the Q-learning algorithm. So yeah, let's do that. Okay, so Epson is redefining his question. He says, I mean, is the laser being sampled for comparison later or when the robot is running live? Okay, so I don't understand this question. Scamiambas, so please, Epson Warco, please rephrase your question. And Scamiambas, he says, can you say again the Gazebo sonar sensor you mentioned? Yeah, so it's a plugin. It's the sonar plugin. Just look, search in Gazebo sonar plugin, and that's all. You will find it there. And Epson, if you have any rephrase of your question, I'm waiting here for 1 minute. Otherwise, I'm providing you on the chat right now my email. And please send me an email indicating that you want to participate in the live programming of OpenAI with Gazebo, with a robot, on the next ROS live show. So I will send you some files, so you will be able to be prepared, and we will start with something that is already prepared. So constructsim.com. Here it is. So there it is, and then let's do a second session of OpenAI with Gazebo, with robots, based on ROS, next week. And thank you very much, but we don't have more time because today was exhausting. This is a complex subject, I know, and we have to finish here today. So we'll keep the questions, the additional questions, and also the description of Dynamic Reconfigure by Sam Pfeiffer for the next week, okay? I'm sorry, we don't have more time. Thank you very much, everybody. Just one question, just one thing more. Remember that we are publishing one new video teaching how to do things with ROS every day, one new video every day. So please subscribe to our channel if you like this kind of stuff. So, and then press the bell, so you will be notified when a new video is published. So thank you very much for attending. See you next week on the number 7, and hopefully with better sound. Cheers.